Hello there. My name is Alara, and welcome to the Late Night Science Channel. Tonight, we're going to talk about something remarkable. Out there in space, beyond our atmosphere, beyond our solar system, astronomers have discovered things that don't make sense. Not science fiction, not speculation, but real observations. Things we've seen, measured, photographed. Things that are actually out there right now, doing whatever strange thing they do, and we don't know why. Before we begin this journey, if you enjoy these peaceful explorations of cosmic mysteries, a like or subscribe would really motivate me to create more videos. Now, let's drift into the unknown together. Think about this. The universe is vast, far larger than we can truly comprehend. And in that vastness, we keep finding surprises, things that challenge what we thought we knew, things that remind us how much remains unexplained. Tonight, we're going to explore these mysteries, not with urgency or excitement, but peacefully, gently, letting each one wash over you like waves on a shore. Some of these discoveries are decades old, still unexplained. Others are recent, just now being studied. All of them share one thing. They're genuine puzzles waiting for someone to solve them. Let's begin with something that happened on a summer night in 1977, August 15th. A man named Jerry Ehrman was working at the Big Ear Telescope at Ohio State University. The telescope was part of SETI, the search for extraterrestrial intelligence, scanning the sky day after day, listening for radio signals that might indicate intelligent life somewhere out there. Most days brought nothing unusual, just background noise from space, the random static of the cosmos. But on this particular day, Ehrman was reviewing printouts of data when he saw something that made him stop. A sequence of numbers that was clearly different from everything around it. The signal was strong, 30 times stronger than the background noise. It came from a specific direction in space, from the constellation Sagittarius, and it lasted exactly 72 seconds. Ehrman grabbed a red pen and circled the sequence. Next to it, he wrote one word: wow. That's why we call it the wow signal. Not an official designation, just one person's spontaneous reaction to seeing something unexpected. And nearly 50 years later, we still don't know what it was. Here's what makes the wow signal so intriguing. Its frequency was around 1420 megahertz, right near what astronomers call the hydrogen line. This is a natural frequency associated with hydrogen atoms, the most common element in the universe. If you were an alien civilization trying to send a signal that others might recognize, choosing a frequency related to hydrogen would make sense. It would be like using a universal language, something everyone would know. The Big Ear Telescope had two receivers that scanned the same patch of sky 3 minutes apart. The signal appeared on the first receiver, but not the second. That means it lasted less than 3 minutes, probably those 72 seconds based on how the data was recorded. Since 1977, astronomers have returned to that same spot in the sky dozens of times. They've used more powerful telescopes. They've listened at the same frequency and nearby frequencies. They've searched patiently for any sign of the signal returning. Nothing. The wow signal was a one-time event. Now, let me be clear about what we don't know. The signal could have been artificial or natural. The Big Ear Telescope couldn't pinpoint locations with great precision, so we know the general direction, but not the exact source. Some scientists have proposed that it might have been a comet. Comets can emit radio waves when solar wind interacts with their hydrogen clouds. In 2016, a researcher suggested that 2 comets were in that region of space at the time. But there's a problem with this explanation. The WOW signal was incredibly narrow band. It occupied a very specific frequency, the kind of precision you'd expect from an artificial transmitter, not from a natural source, which usually produces signals across a broader range. Other scientists have suggested terrestrial interference, maybe a satellite or aircraft, that happened to send a signal at just the right moment. But the big ear was designed to filter out such interference, and the signal came from a direction inconsistent with any known satellite at the time. So what was it? The honest answer is we don't know. Nearly 50 years later, it remains unexplained. If it was an alien civilization, why would they transmit only once? Maybe they were using a lighthouse strategy, sweeping a beam across the galaxy, and we just caught it for a brief moment. Maybe it was a one-time broadcast. Maybe it wasn't meant for us at all, just an accidental spillover from some other communication. Or maybe it wasn't aliens at all. Maybe it was a natural phenomenon we've never encountered before or since. The universe is full of processes that emit radio waves, pulsars, quasars, magnetars, supernova remnants. We're constantly discovering new types of radio sources. Perhaps the WOW signal was something natural that we simply haven't seen again. The truth is, we may never know. The signal lasted 72 seconds in 1977 and never returned. It's a mystery frozen in time, a reminder of how much remains unexplained. Somewhere out there in the direction of Sagittarius, something sent out a powerful, narrow-band radio signal, and we happened to catch it. As you breathe slowly, think about that. The cosmos might have spoken once, and we might have heard it, and we might never hear it again. Let that thought drift with you as we move to our next mystery. Now let's talk about a star that's been puzzling astronomers since 2011. Its official designation is KIC 8462825, but most people call it Tabby Star, named after astronomer Tabitha Boyajian, who led research studying it. Tabby Star sits about 1,470 light-years away in the constellation Cygnus. From a distance, it looks ordinary. It's slightly larger and hotter than our Sun. Nothing about it should make it special. But in 2011, the Kepler Space Telescope noticed something strange. Stars dim sometimes, that's normal. When a planet passes in front of a star from our perspective, the star's light drops slightly. That's how we detect exoplanets, by watching for these tiny, regular dips in brightness. When Earth passes in front of the Sun from another star's perspective, the Sun's light would dim by about 0.01%. Tiny, but measurable. Jupiter, being much larger, would cause the Sun to dim by about 1%. That's the kind of dimming we expect from planets. Regular, predictable, small. Tabby Star doesn't do that. In 2011, its light dropped by 15%. Then it came back. In 2013, it dropped by 22%. Then it came back again. The dimmings were irregular, unpredictable. They didn't repeat at regular intervals. They lasted different amounts of time. Sometimes the star would dim a little, sometimes a lot. 22% is enormous. To block that much light, you'd need something absolutely massive, something as large as the star itself. This discovery set off intense interest. What could be blocking the light? Here's where things got interesting. Someone suggested it might be an alien megastructure. The idea comes from a concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced civilization would do if it needed enormous amounts of energy. Eventually, he reasoned, they might build structures around their star to capture its energy output. Not a solid shell, which would be impossible, but a swarm of energy-collecting satellites. If you were building something like that, it would block varying amounts of starlight as the structure orbited, creating irregular dimming patterns, exactly like what we see with Tabby Star. Now, before you get too excited, most astronomers don't think Tabby Star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here's the thing, scientists had to consider it because they couldn't explain the observations any other way. That's how genuinely strange this star is. So if it's not aliens, what is it? Scientists proposed several natural explanations. Maybe there's a giant swarm of comets orbiting the star. If a family of comets passed in front, they would block light irregularly, their dust tails creating uneven dimming. But there are problems. Where did so many comets come from? You'd need an enormous number to block 22% of the star's light, and comets would produce dust that would make the star appear redder when dimmed. Tabby Star doesn't do that. Its color stays the same. Another theory suggested a recent collision. If two large objects smash together near the star, the debris cloud could block light irregularly as it spreads out. But we'd expect to see excess infrared radiation from warm dust. We don't. Some suggested the dimming might be caused by the star itself, some kind of variable star behavior, but Tabby Star doesn't show the characteristics of known variable stars. Then, in 2017, astronomers caught Tabby Star dimming again and observed it across multiple wavelengths. What they found was interesting. The dimming was more pronounced in blue light than red light. That's consistent with dust scattering. Small dust particles scatter blue light more than red, the same reason Earth's sky is blue. So maybe it is dust after all. But if so, where's it coming from? Why so much of it? Why the pattern so irregular? The latest observations suggest Tabby Star might have a large debris field around it, perhaps from a destroyed planet or massive collision. The debris blocks light irregularly as it orbits. This is currently the leading explanation, but it's not entirely satisfying. And here's what makes this even stranger. Tabby Star is still doing it. We've watched it for over a decade now. It keeps dimming in weird, unpredictable ways. The phenomenon is real, verified by multiple telescopes. Something is actually blocking light from this star in ways that remain puzzling. As of 2025, out of hundreds of billions of stars, this is the only one that behaves like this. As you rest there, think about that star, flickering strangely in the constellation Cygnus, keeping its secret. Let me tell you about something discovered in 2019 that has a perfect name: odd radio circles, or RCs for short. The name captures them perfectly. They're odd, they're circles, and we only see them in radio wavelengths. If you point a radio telescope at certain parts of the sky, you see a perfect circle, enormous, hundreds of thousands of light years across, and usually there's a galaxy at the center. The first one was discovered by a team led by astronomer Ray Norris using the Australian Square Kilometre Array Pathfinder Telescope, ASCAP. They were surveying the radio sky when they found these circular structures. At first, they thought it was a processing error. Circles are suspicious in astronomy. Nature rarely makes perfect circles. But when they checked carefully, the circles were real. They found 3 more. Other telescopes confirmed them. As of 2025, we found about a dozen orcs. They're rare, they're large, and their origin remains a puzzle. Each orc is a ring or shell of radio emission, nearly circular, sometimes perfectly so. At the center, there's usually an elliptical galaxy that appears normal at optical wavelengths. Nothing obvious about it would explain the radio ring around it. The rings are enormous, some more than 1 million light years across. That's 10 times the diameter of the Milky Way. Now, astronomers see circular things in the sky sometimes. Supernova remnants can look circular, expanding shells of debris from exploded stars, but those are much smaller and associated with recent explosions. Orcs are too large and too far away to be supernova remnants. Planetary nebulae can also look circular, shells of gas shed by dying stars, but again, much smaller and in our galaxy. Orcs are definitely not planetary nebulae. Some galaxies have radio lobes where jets from central black holes shoot matter out into space. These can create circular structures when viewed from certain angles, but orcs don't match those characteristics. The central galaxies don't show the active supermassive black holes needed to create such structures. So what are they? Honestly, we don't know. Scientists have proposed several theories. Maybe they're shock waves from massive explosions in galaxy centers. If a galaxy went through intense star formation or its central black hole suddenly became active, it could create a blast wave expanding outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that's the case, why don't we see more of them? Galaxies go through active phases all the time. Another theory suggests they might be related to merging galaxies. When two galaxies collide, maybe the collision creates shock waves that expand as spherical shells. But galaxy mergers are common, orcs are rare. Some scientists have even suggested more exotic explanations. Maybe they're imprints of primordial events from the early universe. Maybe they're related to cosmic strings or other features of space-time. These ideas are pretty speculative. The truth is, we're still in the discovery phase with orcs. We've only known about them for a few years. We need more observations, more data. What makes orcs fascinating is that they represent something genuinely new. We've been studying the radio sky for decades, but orcs only showed up when we built more sensitive telescopes. They were always there, we just couldn't see them. This tells you something important. The universe is full of things we haven't discovered yet, not because they're hiding, but because we don't have the tools to see them. Every time we build a better telescope, we find something unexpected. ORCs are a perfect example. Nobody predicted them. They were a complete surprise. And now astronomers are trying to figure out what they are. As you drift, imagine those giant radio circles out there, glowing invisibly, waiting to reveal their secrets. Now let's talk about something that breaks the rules on a cosmic scale. In 2021 and 2024, astronomers discovered two enormous structures that challenge fundamental principles of cosmology. The first is called the Giant Arc. It was discovered by Alexia Lopez, a PhD student at the University of Central Lancashire. The Giant Arc is a structure of galaxies that spans about 3.3 billion light-years. Not the distance to it, that's how large the structure itself is. Light takes 3.3 billion years from one end to the other. To put that in perspective, the entire observable universe is 93 billion light-years across. This structure is a significant fraction of that. The giant arc appears as a curved arrangement of galaxy clusters, like a giant arc in the sky. Then, in 2024, the same team found something else, the Big Ring. This is another enormous structure, about 1.3 billion light-years in diameter. And here's what's significant. It's in the same region of sky as the giant arc, at roughly the same distance, about 9.2 billion light-years away. Two enormous structures in the same part of the universe suggests they might be related somehow. Now, why is this a problem? In cosmology, there's something called the cosmological principle. This principle states that when you look at the universe on large enough scales, it should be roughly uniform. No matter which direction you look, you should see roughly the same density of matter. The universe should be homogeneous and isotropic at large scales. This principle is fundamental to our understanding of the universe. It's built into the standard model of cosmology, supported by observations of the cosmic microwave background, showing the early universe was remarkably uniform. But the giant arc and big ring challenge this. They're too large. According to calculations based on the standard model, structures shouldn't grow larger than about 1.2 billion light-years. That's the theoretical limit based on how gravity has had time to pull matter together since the Big Bang. The giant arc is nearly 3 times larger than this limit. Even the big ring is pushing the boundary. If these structures are real, and they appear to be, then either our theoretical limit is wrong, or something unexpected is happening. Some astronomers have questioned whether these structures are real or just statistical flukes. When you look at galaxy distributions, you can sometimes see patterns that aren't really there, coincidental alignments. But Lopez and her team did careful statistical analysis. The probability of the giant arc being a random arrangement is about 1 in 6,000. That's pretty low. The structure appears genuine. The big ring statistics are even more compelling, and the fact that both structures in the same region makes coincidence less likely. So what are they? One possibility is that they're related to baryon acoustic oscillations. In the early universe, sound waves traveled through hot plasma. These waves left an imprint on how matter is distributed, creating a preferred scale for structures. But the giant arc and big ring don't match the expected size from these oscillations. They're much larger. Another possibility involves cosmic strings, hypothetical one-dimensional defects in space-time predicted by some theories but never observed. If cosmic strings exist, they could create large-scale structures as galaxies form preferentially along them. But cosmic strings are speculative. We have no direct evidence they exist. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we thought. Maybe the universe has large-scale structure we didn't account for. Maybe at the largest scales, things are more complex than our models predict. That's how science works. Observations, models, and when they don't match, update the models. As of 2025, the giant arc and big ring remain controversial. Some astronomers are convinced they're real structures challenging the cosmological principle. Others are more skeptical. What's clear is that the universe at the largest scales is more complex than we thought. As you breathe slowly, think about these enormous structures, arcs and rings of galaxies stretching across billions of light-years, suggesting the cosmos might be stranger than our theories predict. Let me tell you about a place in the universe that's almost empty. It's called the Boötes Void, and it's one of the strangest features of the cosmic landscape. The Boötes Void is a region of space about 330 million light-years across. To put that in perspective, that's more than 3,000 times the diameter of the Milky Way. It's an enormous volume of space. Here's what makes it strange. This volume should contain about 2,000 galaxies based on the average density of galaxies in the universe. But when astronomers survey the Boötes Void, they find only about 60 galaxies. The rest is empty. Not completely empty, but compared to what should be there, it's remarkably void of matter. The void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping galaxy distribution and noticed this huge empty region in the constellation Boötes. Initially, they weren't sure if it was real or just an artifact of their survey. Maybe they'd missed some galaxies. Maybe their detection methods weren't working properly in that region. But follow-up observations confirmed it. The void is real. There truly is a huge bubble of space with almost no galaxies in it. Now, voids aren't unusual in the universe. The cosmic web consists of filaments of galaxies surrounding voids. Most voids are tens of millions of light-years across, pretty common. But the Boötes Void is special. It's much larger than typical voids, one of the largest known supervoids in the nearby universe. Here's the thing. The universe started out almost perfectly uniform. The cosmic microwave background shows us that at 380,000 years after the Big Bang, matter was spread almost evenly throughout space. There were tiny density variations, incredibly small. Over time, gravity amplified these variations. Regions that were slightly denser attracted more matter and became denser. Regions that were less dense lost matter to surroundings and became voids. Computer simulations of this process can reproduce the cosmic web we see today. Filaments, clusters, and voids all emerge naturally from gravity acting on initial density variations. But the simulations also predict limits. Voids can only grow so large given the universe's age and gravity's strength. The Boötes Void is close to this limit, about as large as voids can theoretically get. That makes it interesting because it's an extreme example, testing our understanding of structure formation. If our models are correct, we shouldn't see voids much larger than Boötes. If we do, it would suggest something's wrong with our models. So far, the Boötes Void fits within theoretical limits, but it's close to the edge, making it worth studying carefully. There's another interesting aspect. The few galaxies inside it are weird. Some are forming stars at unusually high rates. Some have unusual shapes or characteristics. It's like the isolation has affected them somehow. Think about it. If you're a galaxy in a dense region, you're constantly interacting with other galaxies, pulling on them gravitationally, sometimes colliding and merging, exchanging gas. You're part of a busy neighborhood. But if you're a galaxy in the Boötes Void, you're alone. Your nearest neighbor might be millions of light years away. You're evolving in isolation without the gravitational harassment that galaxies in dense regions experience. This isolation might change how you evolve. Maybe you retain more gas because nobody's stripping it away. Maybe your star formation happens differently. The galaxies in the Boötes Void give us a chance to study what happens to galaxies when they're isolated, a natural experiment the universe has set up for us. But the fundamental question remains, why is the Boötes Void so empty? Why did this particular region end up with so few galaxies? The answer probably goes back to the initial conditions of the universe. This region must have started with slightly lower density than average. Over billions of years, gravity pulled matter out of the region toward denser areas, creating the void we see today. But why was this region less dense to begin with? That relates to whatever process created initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally, by chance, you'd get a larger variation. The Boötes Void might be the result of one of these chance larger variations in initial conditions. It's remarkable when you think about it. The emptiness we see today, 330 million light-years across, originated as a tiny quantum fluctuation in the first fraction of a second after the Big Bang. That microscopic variation has been amplified over 13.8 billion years into this enormous supervoid. The universe is strange like that. The smallest things can have the largest consequences given enough time. As you rest there, breathing slowly, imagine that vast emptiness, that cosmic desert where galaxies are rare, a monument to chance variations in the infant universe. Speaking of the early universe, let me tell you about one of the most peculiar features in the cosmic microwave background. It's called the CMB Cold Spot, and it's been puzzling cosmologists since 2004. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. When the universe was 380,000 years old, it cooled enough that electrons and protons could combine to form neutral hydrogen. Before this, the universe was opaque. Photons couldn't travel far before hitting free electrons. After this, the universe became transparent. Photons could travel freely. The CMB is made of these photons, traveling through space for 13.8 billion years. We see them today as faint microwave glow coming from all directions. The remarkable thing about the CMB is how uniform it is. If you measure its temperature in different directions, it's almost exactly the same everywhere, about 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations, some regions slightly warmer, some slightly cooler, temperature differences about 1 part in 100,000. These variations are imprints of density fluctuations in the early universe. Regions that were slightly denser were slightly cooler in the CMB. These dense regions eventually became galaxies and galaxy clusters we see today. So the CMB is incredibly important, a snapshot of the universe at 380,000 years old. Satellites like COBE, WAMAP, and Planck have mapped it in exquisite detail. And when scientists analyzed these maps, they found something unexpected. There's a region of the sky about 10 degrees across that's significantly cooler than expected. This is the CMB Cold Spot. It's not just a little cooler, it's about 70 millionths of a degree cooler than average. That might sound small, but in the context of the CMB's tiny variations, it's huge. The cold spot is located in the constellation Eridan. It's oval-shaped, spanning about 10 by 5 degrees, roughly 50 times the apparent size of the full moon. Here's why it's strange. Based on our standard cosmology model, we can calculate the probability of such a large cold region appearing by chance. The probability is 2%, not impossible, but unlikely. 2% means if you ran the universe 100 times with random initial conditions, you'd expect to see a cold spot like this in about 2 of those universes. We live in one universe, so either we're just unlucky and happen to be in the 1 in 2%, or there's something special about the cold spot. Scientists have proposed several explanations. One idea is that the cold spot is caused by a supervoid. Remember, voids are regions with few galaxies. If there's an enormous void between us and the CMB in this direction, photons passing through it would lose energy due to something called the integrated Sachs-Wolf effect. As photons enter a void, they climb out of a gravity well, losing energy. As they leave, they fall into a well, gaining energy. If the universe weren't expanding, these would cancel out. But because the universe is expanding, the void gets larger and less dense while photons cross it. They gain less energy leaving than they lost entering. Net result, cooler photons. So a supervoid could create a cold spot in the CMB. And indeed, astronomers have found evidence of a large void in that direction. But here's the problem. Even with this void, calculations suggest it can only account for a small part of the cold spot's coldness. You'd need an absolutely enormous void to explain the full effect, and we don't see evidence of a void that large. Another theory suggests the cold spot might be related to a collision between our universe and another universe in a multiverse scenario. In some versions of cosmic inflation theory, our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early on, it would leave a mark in the CMB, a circular region colder or warmer than average. This is a pretty exotic explanation, and there's no direct evidence beyond the cold spot itself. but it shows how puzzled scientists are. They're willing to consider multiverse collisions because conventional explanations don't quite work. A third possibility is that the cold spot is just a statistical fluke. 2% probability means it's rare but not impossible. Maybe we just happen to live in a universe where this unlikely feature exists. Sometimes rare things happen. The challenge is we only have one CMB to observe. We can't run the experiment again. We can't create 100 universes and see how many have cold spots. We have one data point, the universe we live in. This makes it hard to know if the cold spot is meaningful or just chance. As of 2025, the CMB Cold Spot remains unexplained. It might be caused by a supervoid, but probably not entirely. It might be a statistical fluke, but that seems unsatisfying. It might be evidence of exotic physics, but that's highly speculative. What's clear is that it's anomalous. It stands out in CMB maps. It's larger and colder than our models predict. And until we have a convincing explanation, it remains one of the strange things we don't fully understand. As you drift, imagine that cold patch in the ancient light, that darker region in the baby picture of the universe, holding some secret we haven't yet deciphered. Now let's talk about a star that breaks the rules of nuclear physics, or at least seems to. It's called Przybylski's star, officially designated HD 101065. It's located about 370 light-years away in the constellation Centaurus. From a distance, it looks normal. It's an A-type star, about twice as massive as the Sun and about 6 times more luminous. Nothing unusual there. But when astronomers analyzed its light spectrum, they found something absolutely bizarre. The star contains elements that shouldn't exist in any star for more than a few weeks. Specifically, it contains technetium, promethium, and other radioactive elements with short half-lives. Let me explain why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. The process continues in the most massive stars, creating heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, incredible pressures and temperatures create heavy elements scattered into space where they can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed, born from a cloud of gas containing material from previous generations of stars. But here's the catch. Some heavy elements are radioactive. They decay over time. Uranium has a half-life of about 4.5 billion years. That means half of any uranium will decay into lighter elements in 4.5 billion years. Even after billions of years, some uranium is still around. Technetium, on the other hand, has no stable isotopes. All forms are radioactive. The longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That's nothing on cosmic timescales. Przybylski's star is probably several billion years old. Based on its characteristics, it's a mature star. If it formed with technetium in its atmosphere, that technetium would have decayed away billions of years ago. There should be none left. Yet, when astronomers observe the star's spectrum, they see clear evidence of technetium. They also see promethium, another radioactive element with a short half-life. And they've seen these elements consistently since the star was first studied in detail in the 1960s. So where is this technetium coming from? There are a few possibilities, none completely satisfying. One idea is that the star is creating technetium on its surface through some unknown nuclear process. Maybe there's a mechanism we don't understand producing these elements in the star's atmosphere. But this seems unlikely. We have pretty good understanding of nuclear physics, and there's no known process that could do this in the cool outer layers of a star. Another idea is that technetium is being brought up from the star's interior. Maybe deep inside, nuclear reactions are creating technetium, and convection currents are carrying it to the surface. But again, this doesn't quite work. The star's interior isn't hot enough to create technetium through normal nuclear reactions. A third idea, which sounds like science fiction, is that the star contains super heavy elements with atomic numbers far beyond anything we've seen. In theoretical nuclear physics, there's something called the island of stability. The idea is that if you go far enough up the periodic table beyond known elements, you might find a region where certain super heavy elements are relatively stable. Some of these, if they exist, might decay into technetium or promethium as intermediate products. So the star might contain super heavy elements slowly decaying, replenishing the supply of technetium and promethium. This is highly speculative. We've never observed super heavy elements in nature. We've created a few in particle accelerators, but they decay almost instantly. The island of stability is a theoretical prediction, not established fact. Still, Przybylski's star is so weird that astronomers are willing to consider exotic explanations. Another strange thing about the star is its composition. It has unusually high amounts of certain rare Earth elements. Its spectrum shows strong lines of holmium, dysprosium, and europium. These elements are much more abundant in Przybylski's star than the Sun. It's what's called a chemically peculiar star. There are several types of chemically peculiar stars, thought to arise because atmospheric processes concentrate certain elements. Radiation pressure and magnetic fields can cause some elements to sink or float in the star's atmosphere, creating unusual abundances. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are more extreme than almost any other star, and the presence of short-lived radioactive elements is unique. Some astronomers have wondered if it might have a companion, maybe a neutron star or white dwarf, with material from the companion falling onto Przybylski's star, bringing radioactive elements. But we see no evidence of a companion. The star's motion doesn't show the wobble we'd expect from an orbiting partner. As of 2025, Przybylski's star remains a mystery. For more than 60 years, astronomers have observed it. For more than 60 years, it's shown technetium and promethium in its spectrum. These elements should have decayed away long ago, yet they're still there. Either there's a nuclear process we don't understand, or the star contains exotic matter, or there's something fundamentally wrong with our observations or interpretations. None of these options is particularly satisfying, which is why Przybylski's star is one of the strangest objects in the sky. As you drift, imagine that cold patch in the ancient light, that darker region in the baby picture of the universe, holding some secret we haven't yet deciphered. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii detected something moving through the solar system. At first, they thought it was a comet or asteroid, but as they gathered more data, they realized this object was different, very different. They named it Oumuamua, a Hawaiian word meaning scout or messenger, and it was the first confirmed interstellar object to pass through our solar system. Oumuamua came from outside the solar system, from interstellar space. It approached from the direction of the constellation Lyra, passed through the inner solar system, and headed back out into interstellar space. We only had a few weeks to study it before it became too faint and distant to observe. What we learned during those weeks was fascinating and confusing. Oumuamua was strange, really strange. First, its shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated. Best estimates suggested it was about 400 meters long and only about 40 meters wide, a ratio of 10 to 1. It's cigar-shaped, or maybe more like a pancake, depending on exact geometry. This is unusual. Most asteroids and comets are more spherical or irregular, not long and thin. An elongated shape like Oumuamua is possible, but rare. Second, its surface. Oumuamua was reddish in color, similar to some objects in the outer solar system, suggesting its surface had been exposed to cosmic rays for a long time, which can redden surface material. So far, normal. But Oumuamua showed no signs of a coma. Comets, when they get close to the sun, heat up. Ice on their surface vaporizes, creating a cloud of gas and dust called a coma. It's what gives comets their characteristic appearance. Oumuamua didn't have a coma. Even when it passed close to the sun, well inside Mercury's orbit, no coma appeared. This suggested it wasn't a comet, at least not a typical icy comet. Maybe it was more like an asteroid, made of rock or metal. But then came the really weird part. Oumuamua's trajectory didn't match what we expected. After it passed the sun and was heading back out of the solar system, it was accelerating slightly more than it should have. When you calculate an object's trajectory, you account for gravitational pull of the sun and planets. Those forces are predictable. Based on gravity alone, we could predict exactly where Oumuamua should be at any given time. But it was moving slightly faster than expected. It was being pushed by something other than gravity. This is normal for comets. Evaporating gas from a comet's coma creates a rocket effect, pushing the comet slightly. This non-gravitational acceleration is well understood for comets. But Oumuamua didn't have a coma, so what was pushing it? Scientists proposed several ideas. Maybe Oumuamua was outgassing, but the gas wasn't carrying enough dust to create a visible coma. Maybe it was venting gas from one side, creating thrust, but we just couldn't see it. Some observations suggested there might be very faint traces of gas, but it's hard to be sure. Another idea was that Oumuamua was being pushed by sunlight. All objects in the solar system experience radiation pressure from the sun. Photons hit objects and transfer momentum, pushing them slightly. For most objects, this force is tiny, much smaller than gravity. But if an object is very thin and light, like a sheet or sail, radiation pressure can be significant. Maybe Oumuamua was very thin, more like a pancake than a cigar. If it was only a few meters thick but hundreds of meters across, and if it was made of relatively light material, radiation pressure could explain the observed acceleration. But this raises questions. How would such an object form naturally? Why would it be so thin? It's hard to imagine natural processes creating a thin, rigid sheet of rock or ice hundreds of meters across. This is where things get really speculative. In 2018, two Harvard astronomers, Abraham Loeb and Shmuel Bialy, published a paper suggesting that Oumuamua might be artificial. Specifically, they suggested it could be a light sail, a thin, reflective sheet designed to be pushed by starlight. Such a sail could be a spacecraft or probe sent by an alien civilization. This suggestion generated enormous controversy. Most scientists were skeptical. The alien hypothesis is always the last resort in astronomy. You only invoke aliens when you've exhausted all natural explanations. And there were natural explanations for Oumuamua, even if they were a bit strained. Loeb argued that we should at least consider the possibility. If Oumuamua was artificial, it would be the most important discovery in human history. The fact that it's unlikely doesn't mean we should dismiss it without consideration. But most astronomers think Oumuamua is natural, probably a comet with unusual properties, or an asteroid with a weird shape, or maybe a piece of a shattered planet from another star system. These explanations require fewer assumptions than aliens. The problem is, we'll never know for sure. Oumuamua is gone, too far away and too faint to observe now. We had a few weeks to study it, and we didn't get all the data we wanted. If another interstellar object passes through our solar system, we'll be better prepared. We'll have more telescopes ready to observe it. We'll get more detailed data. In fact, a second interstellar object was discovered in 2019 called Boötes, and it's definitely a comet. It has a coma and tail and behaves exactly like comets in our solar system do. Boötes is unremarkable, which makes it remarkable. It shows that interstellar comets are pretty much like solar system comets. But Oumuamua remains unique. We've never seen another object quite like it. Maybe it was just a weird natural object. Maybe it was something more. We'll probably never know. What's clear is that interstellar objects pass through our solar system occasionally. The galaxy is full of asteroids and comets ejected from their home star systems. They drift through interstellar space. Some, by chance, pass through our solar system. We can detect them now, and every one we detect teaches us something new about the universe beyond our sun. As you drift towards sleep, think about Oumuamua, that strange visitor from another star system, tumbling through our neighborhood and vanishing back into the dark, carrying its secrets with it. In June 2018, telescopes around the world detected a bright explosion in a galaxy 200 million light-years away. They labeled it AT2018 COW. The name comes from the automated naming system for astronomical transients. The cow part is just random letters, but it became the nickname for this event. At first, astronomers thought it was a supernova. Supernovae are exploding stars, happening regularly. We detect them dozens every year. But as they gathered more data, they realized AT2018 COW was different, very different. First, it was extremely bright, about 10 to 100 times brighter than a typical supernova. And it got bright fast. Most supernovae take weeks to reach peak brightness. AT2018 COW reached peak brightness in just days. Then it faded quickly. Most supernovae remain visible for months, gradually fading over time. AT2018 COW faded in weeks. It was like someone turned on a cosmic flashlight, shined it for a brief moment, and turned it off. The spectrum was also unusual. It didn't match known types of supernovae. The temperatures were extremely high, tens of thousands of degrees, and the explosions seemed to be expanding very fast, at a significant fraction of the speed of light. Astronomers were baffled. What kind of explosion could be this bright, this fast, this hot, and this different from anything they'd seen before? They quickly realized AT2018 COW wasn't alone. As they looked through archival data and continued monitoring the sky, they found more events like it. These ultra-fast, ultra-bright transients seem to be a whole new class of astronomical events. They're sometimes called fast blue optical transients, or FBOTs. The name describes them well: fast, peaking and fading in days or weeks; blue, emitting lots of ultraviolet light indicating high temperatures; and optical transients, appearing and disappearing in visible light. As of 2025, we've found a few dozen of these events. Not many, maybe several dozen. They're rare, or at least rarely detected, and we still don't fully understand what causes them. Several theories have been proposed. One idea is that they're the birth of black holes or neutron stars. When a massive star dies, its core collapses. If the core is heavy enough, it forms a black hole. If lighter, it forms a neutron star. This collapse releases enormous energy. Normally, most energy goes into blowing apart the star's outer layers, creating a supernova. But in some cases, maybe the energy is released differently. Maybe it creates a jet that punches through the star's outer layers and shoots out into space. This jet would create a bright, fast transient that looks different from a normal supernova. Another idea is that FBOTs are the result of a star being torn apart by a black hole. This process is called tidal disruption. If a star wanders too close to a black hole, the black hole's gravity rips the star apart. The stellar material spirals into the black hole, heating up and emitting enormous amounts of energy. Tidal disruption events are known to occur, and they can be very bright. But most are slower than FBOTs. They take months to peak and fade. FBOTs are much faster. Maybe FBOTs are a special type of tidal disruption, where a small black hole disrupts a white dwarf or neutron star. The dynamics would be different, potentially explaining the speed and brightness. A third idea involves interactions between two compact objects. Maybe a white dwarf collides with another white dwarf or a neutron star. The collision would release enormous energy in a brief burst, creating an FBOT. The truth is, we don't know. FBOTs are so new that we're still figuring out their basic properties. Every new detection gives us more data, helping narrow down possibilities. What's exciting about FBOTs is that they represent something genuinely new. Astronomy has been studying supernovae for centuries. We've developed detailed models of how different types work. We thought we understood exploding stars pretty well. Then along comes AT 2018 Cow, breaking all the rules. It's brighter, faster, and different from anything we expected. It forced astronomers to realize there are types of cosmic explosions they hadn't anticipated. This happens sometimes in science. You think you understand something, and then nature throws you a curveball. You detect something that doesn't fit your models. That's when science gets really interesting, because it means there's something new to learn. As telescopes get better and we monitor more of the sky more often, we'll probably detect more FBOTs. Each one gives us clues. Over time, we'll figure out what's causing them. But right now, in 2025, they remain one of the strange, unexplained phenomena in the universe. As you rest there, breathing slowly, think about those cosmic flashbulbs going off across the universe, brilliant and brief, mysteries waiting to be solved. Let me tell you about a star that shouldn't exist. Its official name is HD 140283, but astronomers call it the Methuselah star, named after the biblical figure who supposedly lived to be 969 years old. The Methuselah star is about 190 light-years away from Earth, visible with binoculars if you know where to look, in the constellation Libra. It's an old star, a subgiant, meaning it's exhausted hydrogen in its core and is starting to evolve off the main sequence. Stars like this are ancient, formed in the early universe when conditions were different from today. By studying them, we can learn about the universe's history. Astronomers can estimate a star's age using several methods. One looks at composition. The universe started with almost pure hydrogen and helium. Over time, stars created heavier elements through nuclear fusion and supernova explosions. These heavy elements, which astronomers call metals, accumulate over time. So a star with very few metals probably formed early, before many generations of stars had enriched the interstellar medium with heavy elements. The Methuselah star has very low metallicity, about 250 times less iron than the Sun. This suggests it formed early, when the universe was young and heavy elements were rare. Another method estimates age by looking at the star's nuclear fuel consumption. Stars fuse hydrogen into helium in their cores. Once they run out of hydrogen, they start fusing helium into heavier elements. The rate of these reactions depends on the star's mass and composition. By observing a star's properties, temperature, luminosity, composition, you can estimate how long it's been burning and therefore how old it is. When astronomers applied these methods to the Methuselah star, they got an uncomfortable result. The age of the star came out to around 14 billion years, with error bars that uncomfortably overlap with the age of the universe itself. Here's the problem. The universe itself is only about 13.8 billion years old. We know this from multiple independent measurements. The cosmic microwave background, the expansion rate of the universe, the ages of the oldest star clusters all point to an age of about 13.8 billion years. So how can a star be around 14 billion years old in a 13.8 billion year old universe? The error bars technically allow for ages just barely younger than the universe, cutting it incredibly close, but technically possible. If the star formed very soon after the Big Bang, within the first few 100 million years, it could be that old. But even this is uncomfortable. The very first stars in the universe were different from stars today. They formed from pure hydrogen and helium with no heavy elements. These first stars were probably very massive and short-lived. The Methuselah star doesn't fit the profile of a first-generation star. Second-generation stars, formed from gas enriched by the first supernovae, would have some heavy elements. The Methuselah star has a small amount, consistent with being a second-generation star. But second-generation stars wouldn't have formed immediately after the Big Bang. It would take time for the first stars to live, die, and enrich the interstellar medium, maybe a few 100 million years. So the Methuselah star probably formed at least a few 100 million years after the Big Bang. That would make its maximum possible age about 13.5 billion years, or less. The problem is, the observations keep suggesting it's older than that. Even with improved measurements and refined models, the star's age estimate stays around 14 billion years. The error bars have gotten smaller over time, which is the opposite of what we'd hope. We'd like the error bars to encompass a younger age that's comfortable. So what's going on? There are a few possibilities. One is that our models of stellar evolution are wrong in some subtle way. Maybe low metallicity stars evolve differently than we think. Maybe there's a process we don't understand that affects their nuclear burning rates. Another possibility is that our distance measurement to the star is wrong. Age estimates depend on knowing the star's luminosity, and luminosity estimates depend on knowing the distance. If the star is closer or farther than we think, its age estimate would change. Astronomers have measured the distance using parallax. As Earth orbits the Sun, nearby stars appear to shift position against the background of more distant stars. By measuring this shift, you can calculate distance. The Gaia satellite has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But there's still some uncertainty. Maybe the distance is slightly different than we think, enough to bring the age estimate down to something more comfortable. A third possibility is that the star is simply younger than the best estimates suggest, and we're just on the unlucky end of the statistical distribution. When you measure something with uncertainty, sometimes the true value is at the edge of the error bars. Maybe the Methuselah star is really 13.5 billion years old, and the 14 billion year estimate is just a statistical fluctuation. As of 2025, the Methuselah star remains uncomfortably old. Astronomers keep refining measurements, hoping to resolve the tension, But for now, it stands as one of the strange things in the universe, a star that, according to our best measurements, seems almost as old as the universe itself. Of course, it can't actually be older. Something about our measurements or models must be off, but figuring out what is taking time. Until we do, the Methuselah star will continue to puzzle astronomers. As you drift toward sleep, think about that ancient star glowing steadily for nearly the entire age of the universe, a cosmic elder keeping secrets about its true age. Now, here's something interesting to think about. All of these strange discoveries might seem unrelated. A radio signal from the 1970s, a star that dims irregularly, giant radio circles, structures that are too large, empty voids, cold spots in ancient light, radioactive elements in a star, an interstellar visitor, weird explosions, an impossibly old star. They seem like completely separate mysteries, but maybe they're not. Maybe they're all telling us the same thing, that the universe is more complex than our current models suggest, that there are processes, phenomena, or physics we don't fully understand yet. Think about it. The WOW signal tells us there are radio sources we haven't identified. Tabby Star tells us stars can behave in unexpected ways. Odd radio circles tell us galaxies can create structures we're only beginning to see. The giant arc and big ring tell us the universe might not be as uniform as we thought. Each mystery on its own is just an oddity, something strange we need to explain. But taken together, they paint a picture of a universe that's still surprising us, still showing us things we didn't expect. This is actually normal in the history of science. When you're at the edge of understanding something new, you start seeing anomalies, things that don't quite fit. At first, they seem like isolated problems, but eventually someone connects the dots. Someone realizes these anomalies are all symptoms of something bigger, something we haven't understood yet. That's how we discovered relativity. In the late 1800s, there were several problems in physics. The orbit of Mercury didn't quite match predictions. The speed of light seemed constant regardless of how you measured it. This didn't make sense. Why would everything be moving away from us? Are we at the center of the universe? But as they thought about it more, they realized this pattern would happen if the universe itself was expanding. If space itself was stretching, then galaxies would move apart, and the ones farther away would appear to move faster. This observation led to the Big Bang Theory. The entire universe started from a single point and has been expanding ever since. Nobody expected that. It contradicted the prevailing view that the universe was static and unchanging, but the observations forced astronomers to change their minds. In the 1960s, astronomers discovered quasars, points of light that looked like stars but had strange properties. They were incredibly bright, brighter than entire galaxies, and very far away, billions of light years distant. Nothing we knew about stars could explain how they could be so bright. Eventually, scientists realized quasars weren't stars at all. They were the centers of galaxies containing supermassive black holes. Matter falling into these black holes released enormous amounts of energy, creating the brightest sustained sources of light in the universe. This discovery changed how we thought about galaxies. We realized most large galaxies have supermassive black holes at their centers. These black holes play a crucial role in galaxy evolution. None of this was known before quasars forced us to reconsider what was possible. In the 1980s, astronomers measuring the universe's expansion expected to find it was slowing down. Gravity from all the matter in the universe should be pulling everything back together, slowing the expansion. But when they made careful measurements using distant supernovae, they found the opposite. The expansion was accelerating. This made no sense. What could be pushing the universe apart? This observation led to the concept of dark energy, a mysterious force that makes up about 68% of the universe's total energy. We still don't really know what dark energy is, but we know it exists because the observations demand it. Each of these discoveries started with an observation that didn't make sense, something that contradicted expectations. And each time, instead of ignoring the observation or assuming it was wrong, astronomers followed where the evidence led. They changed their theories to match reality. That's what's happening now with the mysteries I've described. We have observations that don't fit our current understanding. We could ignore them, assume they're measurement errors or statistical flukes, but that's not how science works. Instead, we take them seriously. We study them carefully. We try to understand them. And maybe, just maybe, they'll lead to the next big breakthrough in our understanding of the universe. The reason we're finding so many strange things in space right now isn't because the universe suddenly got stranger, it's because our tools got better. We can see things we couldn't see before. We can measure things we couldn't measure before. Think about the WOW signal. It was detected by a radio telescope in 1977. That telescope was relatively simple by today's standards. Today, we have much better radio telescopes. The Very Large Array, the ALMA array, the upcoming Square Kilometer Array, which will be the most sensitive radio telescope ever built. If the WOW signal happened today, we'd learn so much more about it. We'd know exactly where it came from. We'd know its properties much more precisely. We might even be able to figure out what caused it. The same is true for all these mysteries. We're finding them because we have better tools, and as our tools continue to improve, we'll find more. We'll also understand the ones we've already found much better. Tabby Star was discovered by the Kepler Space Telescope, which launched in 2009. Kepler monitored more than 150,000 stars continuously for several years, looking for exoplanets. Before Kepler, we couldn't do this kind of monitoring. Tabby Star's weird dimming pattern would have been nearly impossible to detect. Now we have TESS, the James Webb Space Telescope, ground-based telescopes with adaptive optics. Each gives us new ways of looking at the universe. And the more ways we look, the more strange things we find. In the coming years, we'll have even better tools. The extremely large telescope being built in Chile will have a 39-meter mirror. The Square Kilometer Array will have a collecting area of 1 square kilometer, 50 times more sensitive than any current radio telescope. NASA is planning new space telescopes to study exoplanets, the early universe, dark matter. Each will have the potential to discover something unexpected. And here's the thing, every time we build a better telescope, we find surprises. Every single time. There's never been a case where we built a more sensitive instrument and found exactly what we expected and nothing more. The universe always surprises us, so we can be confident that in the coming decades, we'll discover more strange things, more mysteries to puzzle over, more observations that don't quite fit our theories. And that's exciting because mysteries drive progress. Let me tell you something about the people who study these mysteries. They're not distant, super-intelligent beings who have everything figured out. They're regular people who get excited when they find something weird, who stay up late trying to understand confusing data, who argue with each other about what observations mean. When Jerry Emmons saw the WOW signal in 1977, he was reviewing paper printouts of data. The Big Ear telescope recorded data on paper, numbers indicating signal strength. Most of the time, the numbers were low, background noise. But on this particular printout, there was a sequence clearly different, much higher than background. Emin grabbed a red pen and circled the sequence. Next to it, he wrote, "Wow." He was genuinely surprised and excited. That human reaction, that sense of wonder, is still part of astronomy today. When Tabby Star was discovered, the astronomers studying it were genuinely puzzled. They knew they were seeing something unusual. They worked hard to explain it. When conventional explanations didn't work, they had to consider unconventional ones, including the possibility of an alien megastructure. That suggestion was controversial. Many scientists criticized it, thought it was irresponsible to mention aliens when there were potential natural explanations. But the scientists who proposed it weren't saying it definitely was aliens. They were saying they couldn't rule it out. And that's honest. When you have an observation you can't explain, you have to consider all possibilities, even unlikely ones. This is what science looks like from the inside. It's not smooth where everyone agrees. It's messy. People disagree, debate, argue about interpretations. They propose ideas that turn out wrong. But through all this mess, progress happens. The scientists studying Przybylski's star have been puzzled for decades. They've proposed many explanations for the radioactive elements in its atmosphere. None quite work, but they keep trying, keep making observations, keep refining ideas. That persistence is what drives science forward, not giving up when things are confusing, keeping at it, trusting that eventually, with enough work, understanding will emerge. And sometimes it takes a long time. The cosmic microwave background was discovered in 1964, but it took decades before scientists really understood what they were seeing. The CMB Cold Spot was noticed in the early 2000s. It's now 2025. We've been studying it for more than 20 years. We still don't fully understand it, but we're not giving up. We keep observing, keep thinking, keep trying to figure it out. That's what science requires. Patience, persistence, a willingness to live with uncertainty. These aren't easy things. It's much more comfortable to have answers than questions. But the universe doesn't care about our comfort. It is what it is. Our job is to observe it as carefully as we can, measure it as precisely as we can, and try to understand it as best as we can. And when we can't explain something, we say so. We admit we don't know. We keep observing, keep measuring, keep thinking, because that's how progress happens. Not by pretending we understand everything, but by being honest about what we don't understand. The strangest things we've discovered in space are strange precisely because they don't fit our current understanding. They're outliers, anomalies, puzzles. But puzzles can be solved. Maybe not today, maybe not tomorrow, but eventually, with enough observation and thought, we figure things out. So the next time you hear about a strange discovery in space, don't think of it as a problem. Think of it as an opportunity to learn something new, to expand our understanding. Because the universe is full of strange things. Some we've found, many more we haven't. And each one, when we discover it, teaches us something. That's the adventure of astronomy. That's why people dedicate their lives to studying the cosmos. Because out there in the darkness between the stars, mysteries are waiting. Strange signals, dimming stars, giant circles glowing invisibly around distant galaxies, ancient voids, cold spots in ancient light, radioactive elements that shouldn't exist, interstellar visitors, unexplained explosions, stars older than they should be. These are the things that keep astronomers fascinated, not because they're scared, but because they're curious. And if you've made it this far, if you've listened to all these strange stories, then maybe you're fascinated too. The universe deserves our fascination. It deserves our curiosity. It deserves our best efforts to understand it, because it's strange, wonderfully, beautifully strange, and that strangeness is what makes it worth studying. As you drift off now, as your breathing becomes slower and deeper, as consciousness begins to fade, carry these mysteries with you into sleep. Think about that radio signal that appeared once and vanished. Think about that star flickering inexplicably in Cygnus. Think about those giant circles glowing invisibly around distant galaxies. Think about structures too large to exist. Think about voids almost empty. Think about cold spots in ancient light. Think about stars defying physics, visitors from other star systems, explosions brighter than anything we predicted, stars almost as old as time itself. These mysteries are real. They're out there right now. And somewhere astronomers are working to solve them, observing, measuring, thinking, slowly piecing together the puzzle. Progress is happening, even if it's slow. And one day, these mysteries will be solved. Maybe not all of them in our lifetime, but someday. And when they are, we'll understand the universe a little better. We'll have pushed back the boundary of the unknown just a little further. Until then, they remain invitations. Invitations to wonder, to question, to explore. The universe is full of mysteries, and we're lucky to be here to witness them. If you enjoyed this journey through cosmic mysteries, there's another peaceful exploration waiting for you on the channel. But for now, there's only rest, only the gentle drift into sleep, only dreams waiting in the dark. Good night, and remember, somewhere out there, strange things are happening, things we don't understand yet, things that one day might change everything we know about the cosmos. Sleep well under the stars.